So I'm here on behalf of Google Technical Infrastructure, which is the basis of all technology that goes behind Google Cloud and all of our other services as well. This is the work of many, many people, not just mine. Also, out of the many, many, many buzzwords in networking today, I'm here to talk about one of them, which I think is percolating to the top as we, at least in the current landscape, which is intent. So I'll be talking about why intent, why is it important, what and how to manage intent. Also, I do fully realize I'm between you and coffee, and this is a little bit gory in details, so I'll try my best to keep you guys awake till coffee comes around. So let's dig into this. Let's start with why, and let's start with cloud computing. And I believe that we are heading towards Cloud 3.0, and I've talked about this before in various forums. Cloud 3.0 for us is serverless compute. It's actionable intelligence. It's got ML APIs that you can use. But what does it do from the networking perspective? So if you look at networking, there's a whole bunch of attributes that go into networking for Cloud 3.0. There's seamless telemetry, there's storage disaggregation, there's policies. I'm not thinking about middle boxes, but the one we're going to talk about today is SLOs, which stands for Service Level Objectives. It's actually SLAs without the financial penalty associated with it. And to prove that our money is where our mouth is, this is how we actually prioritize work at Google. Think of it as Maslow's hierarchy of Google networking needs. At the bottom is availability, because if you don't have an available infrastructure, everything else is moot. So above that is manageability. Velocity is key for us. That helps you be competitive. Then stranding, which is efficiency, and then performance comes last. If you have solved all of the bottom four, then you hit performance. So let's start by looking at a logical diagram of what a cloud network looks like, or any cloud network looks like. Starting with the data centers and then the virtualization piece that sits within the data center. And what we are seeing is that deep learning is actually transforming how we design these data centers. And there's actually a fabulous presentation by Jeff Dean that you can actually find on the web called Machine Learning for Systems and Systems for Machine Learning. It's got a pretty good ring to it. It basically talks about systems that you can build to enable machine learning, and then using those same systems to build better machine learning APIs. So it's if and only if kind of a situation here. On the left, you see a TPU2 board that we have released to the public, at least through GCP. On the right, you see a cluster of these TPU boards all connected together to form a compute element, a larger compute element. And the details are actually not important, but what is important for this talk is what we are seeing in the data center is architectural heterogeneity. So earlier, there was this notion that everything is homogeneous and is one big entity, and you can place workloads anywhere and wherever you want. That is actually breaking down quite a bit because of machine learning, because of specialized offloads. And the second bit to remember is architectural velocity. So TPU1, TPU2, there's YouTube needs in terms of video offloads. There's a whole bunch of things coming in where your data center, at least in this case, data center fabric, is undergoing pretty rapid evolution in terms of architecture. So those are key things to remember from this slide. This is roughly what our footprint looks like. And actually, I apologize. This is a little bit older. Some of those blue regions which show up as future have actually already converted to current. But roughly, this is what it looks like in terms of data center presence for GCP. So now what you see in the previous slide is actually a couple of things. All of these data centers connected together through an inter-data center backbone, which we call B4. And this is pretty old from our perspective. This we talked about back in 2013. Urs came up in ONS and talked about this. This is a complete software-defined WAN, which was built back in 2013, like I said. And there are a whole bunch of control elements, again, all SDN-based, that go into building these data centers, building the virtualization, building TE, building this WAN that connects them, that just talk about server-to-server communication. that I showed in the previous slide. If you expand that out a little bit further, we have another WAN, which is B2, which is a user-facing WAN. And then we have the peering edge, which is Espresso, which is, again, SDN-based, which is programmable, and that we talked about in, I think, SIGCOMM a year ago. So this completes our end-to-end picture. So you have user-facing traffic coming in, hits our B2 backbone, hits one of our data centers, and actually do east-west communication over B4, which is our inter-data center WAN. Talking about these two WANs, B2 is 70-plus location, 33 countries. It's carrying more than 25% of internet traffic as we speak. Today, it's a lot of it is YouTube and video. Our B4, which is our internal data center to data center WAN, is actually fatter and bigger than B2, and it carries more traffic. It's growing faster because if you think about it, it's east-west traffic versus user-level traffic, which is north-south. And this is our fiber footprint across the globe. The points in gray are the POPs that we have, more than 100 POPs across the world. The points in yellow, which you cannot see too clearly, are our caching nodes that are scattered throughout the globe. So why did I show all of this? Again, the notion is that at this level of scale, things are breaking all the time, and in all sorts of different and innovative ways. And we laugh about it, but every day things break in new and innovative ways, is things which you hear all the time. So at that level of scale and those kinds of failures, think about the budgets that you have in terms of SLO. So if you're shooting for 4 nines, that's 4 minutes of budget, SLO budget that you have per month. If you're shooting for 5 nines, that's a meager 24 seconds of budget. And that's really, really low. So why is high network availability such a big deal and such a big challenge? Of course, the budgets are really, really low. But beyond that, you are constantly evolving architecture, and we saw that because of artificial and deep learning, but due to a variety of other reasons. We are constantly pushing new software. If you're not pushing software, if you're not evolving, you're not being competitive. So that's happening quite a bit. And we have a goal of new software within the entire network every 2 weeks. Driven by ever-evolving products. I mean, the products are not sitting idle. I mean, there are products that are evolving. They specify new needs and requirements on that infrastructure that sits below. And then, of course, there is scale. There's scale on the topology side, that's shown in green. There's scale on the logical routing connectivity side. There's scale because of heterogeneity in the network. But across all of this, across scale, across architectures, software, what we found, and this I've talked about in a few different venues, is that network evolution, that the fact that you are touching the network, you're evolving the network, and especially if you're trying to do it in a suboptimal way, that causes the most amount of trouble. It's not the bugs in the software, it's not the bugs in the way you've designed the architecture, it's the fact that you are evolving the network, you are operating the network, that causes problems. And 70% of all failures happen when a management operation is in progress, and typically they're not related. So you touch one part of the network and you think, let me put all of my focus on that part of the network, and boom, something else blows up. So it's unrelated changes that can cause and do cause failures. Hence, intent. So if you want your changes to be frequent, and that is desired, if you want high availability, if you want better efficiency and velocity, your infrastructure needs to be intent-driven. So that's the rationale as to why you need intent. Now, how do you go about solving it? And what is it? What is intent? So one of the slides I threw a while ago, and actually I threw that in another forum, and I want to stress here that this is an analogy. This is not a product, it's an analogy. So you would like to build something like a Google Assistant for networking, where you can go in and say, hey, Google, mutate my network from graph A to graph B. And that could be one way of solving the problem. And in this case, your intent is your graph B, that you would want to get to. Of course, there's that iffy issue of safety where you would want to be safe and ensure that this assistant doesn't run amok and just does whatever it pleases. So you would want the ability to roll back, continuously monitor what's happening, and be able to protect the blast radius if things do go bad. So this analogy changes to mutate my network from graph A to graph B, where every change does not exceed delta, and your rate of change does not exceed a row that you define. So how do you go about building such an assistant? And there are two questions here. Question one is this level of abstraction, let's say a graph B, the right level of abstraction? And B, what does it look like? What does this assistant look like? So this could be one possible implementation where you say, let's focus first on what it looks like and then answer the question about the right level of abstraction next. So if you look at, let's say, graph B as my topological intent, and that's my API that goes into this set of services, that feeds into a topology generator, which is shown in green circle, which spits out a planned topology model. Then you marry it with a config intent, and we've talked about OpenConfig here, which does static validation and spits out both a topology as well as config model for your network, which then you need to push throughout your network, and you're feeding your safety policies, the row and the delta, to ensure that these things are happening in a safe way through gRPC to your devices. And then you have a feedback loop through streaming telemetry, and you ensure that things are not going out of whack. So your runtime model is in sync with what you had as a planned model. So in terms of representing these data, we use internally Unified Network Model, or UNM for short, to represent topology intent. We've talked about OpenConfig for config intent and telemetry. And then we have domain-specific languages for policy, for safety policies and other policies. So there is another talk today that goes a little bit deeper by Sriram, that goes a little bit deeper into UNM. So I'm not going to touch too much into UNM, but what I'm going to talk about is roughly, this is what it looks like. So take two routers or two switches and a link that connects them through one port, each on each side. And this is what the model looks like. So if you were to actually describe a topology intent using what I just showed in the previous slide, and if you think about, let's say, a data center, which there are various topologies here, even if you have a simple cloud topology and you want to represent that using UNM, that becomes really, really painful. If a link is that painful, think about what this kind of a topology looks like. So why are we making things so complicated? I mean, why did we do this? You took such a simple one port across two switches, one link, and made it this really complex beast. And then you're complaining that, hey, this thing is too complicated for a data center topology, let alone this entire network. The reason is we want to capture all the information needed to build that automation. No tribal knowledge. So capture all the data flows that you would need to then automate it. And that's the only way to go about it. We really don't expect humans to operate on that data model. It needs to be automated. And if you really want to visualize it, though we don't understand why, because at that scale is not going to tell you much, you can build these visualization tools if you really need it. So then, coming back to question number one, is topology intent really the right level of abstraction? Clearly, the answer is no, because that is too nitty-gritty. So what you really want to do is pull it one level up and say, what I really want the operator to do is say, give me design B. Instead of saying, give me topology B or config B, give me design B. And then you have a constraint solver, which I'll touch upon, which spits out this topology that, again, feeds into the pipeline that we saw earlier. The constraint solver looks somewhat like this. So the human here is defining design constraints. It's defining the design space whether it's data center, what kind of constraints you want on that, whether it's WAN. And then you feed it into the constraint solver, which takes into account the capacity plans that are coming in from your business needs, the SLOs that you have that you need to maintain, the building blocks that could be the kinds of switches, virtual switches, etc., that you have at your disposal, and that spits out your topology intent. And in terms of what the left-hand side looks like, we've already seen the design space for fabrics, data center fabrics. And in terms of design constraints that you're going to specify, it's actually pretty simple at that point. So you would specify, for example, in the data center space, in every pod, every aggregate switch connects to every TOR. You cannot disrupt more than X% of traffic whenever something goes wrong, or whenever you want to bring down something for an operational, for a management operation. So these are the right level of abstractions that you can deal with, and then let the constraint solver worry about the actual topology intent and spitting out UNM at that point. So again, the analogy looks like, hey Google, mutate my network from design A to design B with the safety policies that I had in mind earlier. So if I were to summarize, pretty much what I would say is availability, as we had seen earlier, availability and safety are paramount. Without that, an unavailable infrastructure is actually non-existent. Changes are really hard, but they should be common, because you would want velocity, you would want to be competitive. You don't want to just say, I want to change my network only so often, let's say monthly or quarterly, or even yearly in some cases, because then you're not being competitive. And then to enable this, you need to pick the right level of abstractions for your intent. And a design level makes sense. And then you need to build a rich set of applications to actually manage that intent. So don't try and insert intent in the middle, but build those in the software applications to manage it. That's all I had. So thank you. I can take one or two quick questions.
Yes, maybe, how are we doing for time? Maybe just a couple of quick questions before coffee. Let's take this one.
Hello. So the very good presentation. I'm asking, is the anything open source here? For example, I saw the OpenNL Summit. There's internet-based policy-driven open source like Apex. Have you looked at that? Is there any similarity? So what about the DSL part as well? So do you have any open source right now for this part?
So out of all the 3 data modeling steps that I mentioned, the only thing we have openly talked about and open sourced is the open config bit for config intent and telemetry, streaming telemetry. So you can definitely participate there. The other 2, not yet. And the challenge for us has been to decouple those from the integrated systems we have internally. So it's not that there is no desire to do so, but it's very difficult to separate, especially the DSLs from what we have, and the UNM not yet.
All right, thank you.
Okay, final, if that was one right at the back, maybe just take the final question. Yes, this one, yes.
Should I introduce myself? Hi, my name is Alex Resnick from HP and also chair of ETSIMAC. So thank you very much for a very interesting presentation. I was looking at what you were showing and kind of thinking of the algorithms that run behind it. You're applying it to a network which now looks like it has a couple of dozen nodes. I chair ETSIMAC, so I think of thousands of little nodes, and I was wondering what thoughts you had about how the approaches that you've taken here will scale to those kinds of networks.
Can you repeat the last part?
How the algorithms that actually implement this stuff will scale from the network that you've showed, which is a couple of dozen data centers, to a distributed edge network, which has probably thousands of nodes in even a much smaller geography, right?
Sure.
Can this be leveraged in that much bigger environment in some sense?
Sure. So I'll answer it in 2 parts. One is, if you look at one of our data center designs, actually there are tens of thousands of just switches. And if you think about virtual switches and other logical switches, that's actually a pretty sizable chunk. So scale is not a problem. I think from the edge perspective, we have quite a few caching presence, quite a large caching presence, and also quite a few POPs scattered across the globe. And we are using similar mechanisms for both. Now, one thing I would point out is the constraints that I talked about are not the same when it comes to data center versus WAN versus caching. So the constraints that you feed in, as the algorithms need to be tweaked. So it's not the same, it's not one universal constraint solver, but we have solved it at various points in the network. So it does apply.
Great. Thank you, Vijoy.
Thank you.